So you've seen what the electromagnetic spectrum looks like, and I just want to summarize this. Here is my frequency, low frequency up to high frequency, or over here, low wavelength to high wavelength in the opposite direction. Lowest energy, those are my radio waves. Then I'm going to go to microwaves, then infrared, which is IR, and then I'm going to have a little stretch that's visible. Then I'm going to go ultraviolet, X-rays, gamma rays. For the most part, nobody really needs you to know just where the cutoffs are. I don't know a whole lot of people who have those cutoffs memorized. But the visible over here, we're going to start with red, go to orange, yellow, green actually takes up a pretty broad range, which probably has more to do with just how we receive it than anything else. It does have more to do with that. Green, blue, violet, which helps because infrared just means below red. And ultraviolet means above violet. So we can remember that reasonably easily. Visible light is going to be a small spectrum, a small part of that spectrum. And it looks something like this over here. Red is going to be somewhere in the 700 nanometer range. Orange will be somewhere in the area of 600 nanometers. Yellow is pretty small. Honestly, it's going to be like 575. Green is a pretty broad one, but look in the 550 area. Blue is going to be like 515. And then violet will be somewhere in the 400s, maybe 400. Blue is maybe a bit broader. Blue can be about 500. So we get this spectrum. Once you get out close to that 400 nanometer range, you really can't see this very well at all anymore. It's maybe technically still visible. Same thing with red. Once you get up close to that 700, 740-ish range, you're going to barely be able to see anything. But this is kind of a ballpark idea. Between 400 and 700 nanometers, we're going to be able to see that light, and that's sort of the range that they fall into. I do want to do an example. We had sound waves before, and we said that the speed of that sound wave was equal to a wavelength times a frequency. We can do the same thing with light, but light moves at a speed that is not dependent on a whole lot. It does depend on the medium, but like atmospheric conditions aren't going to affect it a whole lot, and there is an upper limit to the speed that anything can move, and it is the speed of light. So we use the letter C to be the speed of light in a vacuum. And it has a value of 3 times 10 to the 8th meters per second. So if I am told that I have a ray of light and it has a wavelength of 550 nanometers, and I would like to find the frequency, I'm going to say wavelength times frequency equals speed of light. So my frequency is speed of light over a wavelength is 3 times 10 to the 8th meters per second divided by my 550 nanometers. And I do that, and I get a number like 5.45 times 10 to the 14th hertz. I could do the same thing if I said I've got a frequency of my light of, let's say, 9 times 10 to the 6th hertz. I'm going to say my wavelength is c over frequency, so 3 times 10 to the 8th meters per second over 9 times 10 to the 6th hertz. And for that one, I get 33.3 meters. So that's how I'm going to use this quick equation to be able to solve for wavelength or frequency given the other one. And this is just a range of kind of what frequencies or wavelengths rather of light give us visible light. And the kinds of questions that come up with this usually deal with trying to figure out where a certain range falls. So radio waves, these go up to, or these go down to about 1 hertz. So from 1 hertz, our cutoff here to microwaves is something like 10 to the 8th hertz. So if these are my frequencies in hertz. Between microwaves and IR, we are looking something like 10 to the 11th hertz. IR to visible is less than 10 to the 15th, but not a whole lot less. So this range is roughly in the 10 to the 15th hertz area. Between UV and X-rays is something like 10 to the 17th hertz. And between X-rays and gamma rays is going to be something like 10 to the 19th hertz. There's a little bit of wiggle room. It's not like if you have a ray of light that you can 100% say this is 100% an X-ray and not a gamma ray if you are right close to that border. It's a little bit of a loose classification. It doesn't change major properties. It's sort of a range, right? Just like you might look at some color of light and say, well, I don't know if that's really blue or green. It falls right between these wavelengths. It's kind of somewhere between them, and that's okay. If I've got this thing, if I said I found that I had a frequency of 9 times 10 to the 6th hertz, I would say 10 to the 6th hertz lands me here somewhere. Let's do that in red. Lands me here somewhere. This one's going to be a radio wave. This one I've got 5.5 times 10 to the 14th hertz. That one is going to land me somewhere in here, right? This is going to be visible. And I picked it out anyway, 550, to be kind of right in the middle of that green range. One more. If I were given a frequency of, let's say, 10 to the 18th hertz, I could pick out and say 10 to the 18th hertz lands me right here in X-rays. It's an X-ray. So those are the kinds of things that you get with this. They're not particularly complicated. They're just finding where they fall on a range.